Hey, what's up everyone? I'm really excited to bring this next video to you. So let's say we have, this is going to be math episode, I think it's 4 on the channel, but we're going to be going over a really fundamental idea that is related to a lot of topics in math called a geometric sum. So geometric sums already work off principles that you need to know in mathematics, such as a fraction, but I'll go over a fraction really quick. A fraction is essentially a piece of a whole. So let's say you had one apple to yourself, and then your neighbor or your friend had 2 apples, and you wanted to represent this as a fraction. It's hard to explain without using the term again, but let's say we wanted to recognize this not as a number, a whole number. So we didn't want to say we have one apple. We wanted to say we had 1/3 of the groups of apples. So let's say you had 1 apple to his 2 apples would be the ratio, but it allows you to represent the parts that you have of that apple as a non-whole number, but representative in a relationship to what we call the denominator. This is the numerator, and this is the denominator. So geometric sums work off fractions and essentially summing up a lot of fractions that are multiplied together. So let's look at this. So let's say we have a sum of n terms. So we're going to start with the zeroth term, which is going to be a. And then we're going to add a x. And then we're going to add ax squared. And then we're going to add ax cubed all the way up to ax to the n minus 1. And then we're going to have s sub n, which will equal a. And we're going to multiply now by x. Sorry for switching that up there. So now we're going to get this first term. It's not just going to be an a or a constant number. It's going to be a x, and then we're going to get squared, plus all the way up to a x to the n, x to the n minus 1, but now we get a plus 1, so these cancel. And then what you're going to notice here is every term will cancel. Okay, so what we're going to do here, actually, sorry, I skipped a step, is we're going to do something. We're going to do s sub n, and then we're going to subtract x s sub n. And what this allows us to do is a fancy trick, and it's going to allow us to isolate s sub n and calculate what s sub n was originally by doing some algebraic manipulation. Because all of these are going to cancel in a telescoping type fashion. Even this guy will cancel with this guy, and we're going to get just that first term from the first s sub n, and we're going to get the subtraction of ax sub n. And then what can we do here to isolate s sub n? Well, we can just pull out s sub n, and we can have a minus ax sub n. And then s sub n will equal a minus ax sub n, or x raised to the power of n, all over 1 minus x, which can further be reduced to a 1 minus x to the n over 1 minus x. Now, there are some other implications to this formula. So let's say we have a ratio less than 1. So let's say we had 1/2. What happens when we raise 1/2 raised to the power of maybe 1,000? Or we have 1/2 raised to the power of 10 raised to the power of 20. When fractions are less than 1 and you raise them to very large numbers, as you take that nth term, essentially the limit goes to 0. So let's say, we can say that more formally as the limit as x goes to infinity of x sub n, sorry, n goes to infinity, x is less, the absolute value of x is less than 1 equals 0, because it gets smaller and smaller every time. So what we can say here is the limit as s sub n, n goes to infinity, equals a over 1 minus x. This is a fundamental idea. Awesome. So that's the derivation of a telescoping series, but how would we write it in a more, or sorry, not telescoping, geometric sum, but how would we write it in a more like intuitive sense in terms of some summation notation? So let's say we have a summation, so s sub n will equal the summation from n equals 0 to n minus 1. And then we have a x raised to the power of n. This is essentially what we were doing up here. And so how would we write this result? We then have a over 1 minus x, or sorry, a over 1 minus x would be the limit, but we also need the 1 minus x in here if we're just saying the general case. So now let's plug in some numbers and think about this and see if it makes sense. So let's say let's check the first three terms. S sub 3 will equal n equals 0. 3 minus 1 is 2 here. Let's just keep a to be 1 for simplicity's sake and let x be 1/2. What are we going to get here? We'll get 1 minus 1/2 raised to the power of 3 over 1 minus 1/2. There's going to be 1/2 over, I believe this is 7/8, which is going to be 7 over 4, which does not make sense at all, right? So where did I go wrong? Oh, actually this does make sense. I was picking my brain a little bit. So you get 1/2 raised to the power of 0 plus 1/2 raised to the power of 1 plus 1/2 raised to the power of 2, which will equal 1 plus 1/2 plus 1/4, which equals 1 plus 3/4, which equals 7/4. Okay, so that's geometric sums, and I'm going to take the time to make this a 2-part video, and I will teach you a little bit more about maybe a probability, like an application of geometric sums and probability in the next episode, as well as derive a more general case. Notice this is starting from the index where n equals 0. Say, what if we wanted to know the sum I equal, like from the index starting at a to b of maybe c raised to x to the power of I. How would we evaluate this guy? I'm going to leave that up for an exercise. Hopefully you can try it by yourself, but I will be deriving that in my next video. Have a good one, and I hope you all are well. Enjoy your night, enjoy your day, love someone, and peace.